Problem number 7, example 2.8. This is a case for ultimate strength design. The problem states, determine Mn, the nominal or theoretical ultimate moment strength of the beam section shown in the figure, if Fy is 60,000 psi and Fc prime is 3,000 psi. Now, before we can solve this problem, let us first discuss the theory behind ultimate strength design. Now, the theory states like this. Unlike in the working stress, wherein the stress is proportional to the distance from the neutral axis, or in this manner, let me illustrate. If this is your neutral axis, let's say here, neutral axis, for the working stress, the stress is directly proportional to the distance, okay, from the neutral axis to the outermost compression fiber. But for the ultimate moment strength design, it takes into account the realistic, the realistic behavior of concrete, which is in a curved manner or in a parabolic manner. Okay? But a parabola is very hard to calculate. Now, triangle is simple to calculate using ratio and proportion, but a parabola is hard to calculate. That's why this parabola is converted. The theory is introduced by Charles Whitney, and this parabola is converted into a rectangular stress block. And instead of C, wherein C is the distance from the neutral axis to the outermost compression fiber, the value now becomes A, okay, or it is slightly smaller than C by a factor of beta 1. Okay, so that's how they convert the parabola into a rectangular stress block, by introducing A and introducing also the factor beta 1. And this beta 1 is generated from all the experiments that they have done. Okay? So, with that, we can actually determine the total compression force, okay, designated as C. And the total compression force is just the volume of this rectangular stress block. So that you can see clearly, let me illustrate in somehow isometric view. This is now your rectangular stress block. Okay? That is your rectangular stress block. This one is A, and this one is supposedly Fc prime. Okay? But due to all the imperfections in mixing the concrete plus the materials, the aggregates, there are so many factors which can affect the strength of concrete. We only assume 85% of the strength of concrete. So that will be 0.85. So 0.85 Fc prime. Okay? And of course, this one is the width of the beam. This is designated as B. Okay? And the total compression force is just the volume of this rectangular stress block. So volume is length times width times height. So that's why you have 0.85 Fc prime times A times B. Okay? So that is your total compression force. And as for the tension force is simply AS/Fy. Now, we know that in strength of materials, stress is force over area. Okay? And if you want to get the force, that will be simply stress times area. And in the notation of concrete design, this P is your tension force, and this stress is Fy, and area is AS. That's why this formula is written. Okay? So, that's how you account for the forces inside the section of a beam using ultimate moment strength design. Okay? So, let's now put that into practice. Again, let's read the problem. Determine Mn, the nominal or theoretical ultimate moment strength of the beam section, if Fy is 60,000 psi and Fc prime is 3,000 psi. As always, let us account for the given data. B is 14 inches. H is 24 inches, meaning the total height of the beam. D is 21 inches. This is the distance from the centroid of the steel to the outermost compression fiber. AS is the area of steel, 3 pieces of number 9, and the area is given to be 3 square inches. And Fy is 60,000 and Fc prime is 3,000. Okay? So, the first step is to compute tensile and compressive forces. Okay? Tensile and compressive forces. Now, looking back at the figure, we have the formula for tensile, which is this. And we have the formula for compressive, 0.85 Fc prime AB. So, let's compute. For the tensile force, AS times Fy, so I already have the answer here. Let me just pinpoint to the data, no? AS, which is 3, times Fy, which is 60,000. It will generate 180,000 pounds because PSI is in pounds per square inch. So, therefore, the unit here is in pounds. For the compressive, the formula is, in this blue text, the formula is 0.85 Fc prime A times B. Okay? But, unfortunately, we don't know A yet. Okay? We don't know A. Because if this is the neutral axis, and this is C, let's say this is your C, A is smaller than C. Okay, so A will be somewhere here. This is your A. And then this is the stress block. Okay, and then this one will be your tension force, and this one will be your total compression force. And that total compression force is 0.85 Fc prime AB. Okay? Now, T is ASFY, and we can solve this one because AS is given and Fy is also given. So, this is checked. But C, we are not given the value of A. Okay? Our A is unknown. But, this section is in equilibrium. Okay, this section is in equilibrium. And because it is in equilibrium, we can actually equate T equals C. Okay? We can equate T and C. So, therefore, we can equate AS Fy and then equate it to 0.85 Fc prime AB. Okay? And this one will have one equation, one unknown. So, ASFY, we already know this to be 180,000. 180,000. That will be equal to 0.85 Fc prime. Fc prime is 3,000. Let me just substitute directly. Times A. And B is given. Given in the problem to be 14 inches. So, times 14. Now, this is one equation, one unknown. We can solve for A. Okay? So, here, equate T and C and solve for A. So, that's why we were able to solve for A here. Okay? Which is the depth of the compression stress block. Okay? So, A is already checked. And we are now ready to compute the internal moment arm and nominal moment capacity. Okay? Always remember, class, that this section is in equilibrium. This section is in equilibrium. So, therefore, T equals C, and there is also a force couple. No? Force couple between C and T. And the distance between the two is their moment arm. Okay? It is in equilibrium, so there is a force couple between C and T. And then this is the moment arm. Let's call this Y, or moment arm. Okay? Now that moment arm can be calculated because we know this value here to be D. So therefore, the moment arm is equal to D minus this one. This is at the center of your compression stress block. So this value here is A over 2. So D minus A over 2. Alright? So hence, we got this formula here in blue. The moment arm is D minus A over 2. Now, we are given D, which is 21. Here, 21. And A, we were able to compute earlier. So, A divided by 2, and we get this moment arm. And then, because that is a force couple, we can sum up moment about C, and then the moment arm is T times, the moment is T times the moment arm, which is Y. So, T times Y. Okay? So, what is your T? T is 180,000 pounds, and your Y is your moment arm. So, simply multiply the two. If you click here, you can see that it is linked to these two cells here. So, I'm multiplying 180,000 by 18.48 inches. So, you get this answer in terms of pound-inch. And then, if we talk about moment, we always use the unit kip foot. So, therefore, we need to divide this value here by 12,000 so we can generate the answer of 277.18 kip foot. Alright, thank you very much.